We are doing PYQs in a concept-wise. So far, we have seen all this. Resistance-based circuits where it's a one variable question where voltage at the top is an unknown. And then we have seen questions where there is a mix of sources or using source transformation kind of simplifies your life. And then this particular question we noticed circuit given below, what should be the value of resistance R for maximum power dissipation? So we know this is power transfer theorem. And here what we had to do was to convert this. If you treat this as a load, right? You have to convert this as into equivalent Thevenin form. And then there is maximum power dissipation or transfer when you have RL equals. So this is R Thevenin. And then here you have R, this, this load resistance. Typically, this is referred to as load. And this is Vthevenin. Yeah. So far, we know how to go from some circuit. We can go from circuit, to this. In fact, first is we can do this. Thevenin, Norton we can do, right? For the typical circuits where there isn't any dependent thing, right? What is dependency? This is independent. Simple voltage source, simple current source that that is an independent current source. At least for simple circuits, you know how to do this, right? At least for, let's say, simple, that is circuits without any independent things. And here you have maximum power transfer, maximum power dissipation. This happens when your R Thevenin equals RL. Right? This is a condition for this. This also we have seen. So we have seen this. We can also, for example, application of this is in maximum power transfer theorem. So power transfer. What we have to do now is the Wheatstone bridge. So the Wheatstone bridge, let me draw this. Typically you put a sensor inside the bridge and the bridge gets imbalanced. Did we discuss quarter bridge, half bridge and all that? Have we not discussed? When we did bioinstrumentation, when we discussed resistive sensors, did we mention quarter bridge, half bridge, the gauge factor and all that? We have done that. Anyways, at least I will recall that again when we do measurements. But so most of us know what a bridge circuit is, right? Now let's look at a simple bridge, okay? Notice you can draw the bridge in a couple of ways, right? We are used to looking at the bridge this way. So typically you have a voltage source here, and then you have, you try to take off info here. So typically this is referred to as V input. You try to take this output here across this. Okay. So for a balanced bridge, first let's look at the scenario. We have R1, R2, R3, okay, where let's say this bridge we refer to as a balanced bridge. What is a balanced condition? When we say balanced, what do we mean by that? And what is a balanced condition? Balanced bridge. We refer to something as balanced bridge. And then what is this balanced condition? Let me just write this as Wheatstone bridge while I wait for an answer. Wheatstone bridge. What do we refer to as a balanced bridge? And then what do we refer to as what is a balanced condition? When will this balance be active? I think this we have seen in high school. Some of you could recall it. Yes, R3 is equal to R1 open R2. Okay, fine. So this balance condition is R1 by R3. This by this equals this by this, right? You could also write it the other way around, right? Technically, this by this equals this by this. Notice, you take R2 here and then R3 here, right? You get R1 by R2 equals R3 by R. Things in the ratio in the same side. Sorry. Okay, this is a balance condition, but what do we mean? What do you mean by balance here? Can someone also say that? This also implies 1 by R2 equals R3. No voltage generated. Balance bridge essentially says V out is 0. How do you come from here? Now there is no voltage generated, and we also presume if we were to connect this, right, there is no current here. I equals 0. There isn't current any flowing in this bridge. Okay, and then you also have resistant current in the bridge. I bridge is 0. Okay, I bridge is 0. And you could use something like voltage division to actually arrive at this balance. You can find the voltage here using voltage division in the upper arm, voltage division in the lower arm. You can easily arrive at this and use voltage. Now, easiest ways, you could also use some other circuit not drawing. Now, you could also redraw this in a couple of slightly different looking, but the same way. Okay, I mean, same bridge. You could similarly, you could also have a bridge like this, where you could be connecting the power source here, right? And then you could be measuring things here. Take the output here, you can have the power source input source. It is also a Wheatstone. Notice this point and this point, you can, it's a 1 point, right? You can also slightly do some aesthetic changes here. You can have, this is essentially same as this circuit. Here, there is one yellow wire, right? And then from here, there is one rose. There is a single point, right? There is no voltage drop across a wire. It's negligible compared to other resistances here. So we are having one resistance, okay, and then one more resistance. Then we have one more resistance here, and then one more resistance. We try to take the output. All I have done is to make some aesthetic changes, the same circuit, okay. Even this, I have just rotated the circuit, so it's essentially the same circuit. Now, technically, to measure this voltage, you'll have to put some device over there, right? So, you can run into one interesting issue. Let's just read this question, okay? You need to understand something before, we can solve this question. Let's zoom this. The circuit shown below, Vs is 100 volt, this is 100 volt. R1 is 30, R2 is 60, R3 is 90, R4 is 45, R5 is 30. What they want is the current flowing through resistor R3. Quickly, if you look at, is the bridge balanced? Is it balanced? Question number one. Try some of the things that you right. The ratio, this R1 by R4, it's not equal to R2 by R4. The answer is no. Roughly R1 by R4 not equals R2 by R4. But that's not the only issue here. There is also a bigger issue, the finite bridge or an infinite bridge. If you look at the bridge resistance, the second detail that we need to do here is bridge resistance. It can be of two types. It can be finite or infinite. Which of the two scenarios is this one? Is the resistance in the bridge here, right? This R3, is it finite or is it infinite? This is finite here, okay? Interestingly, if you make things, okay, notice, in this case, your I equals 0, easy to handle, okay? Infinite bridge is easy to handle. Okay. Notice, infinite bridge, I equal to 0, this is an easy case, easy problem. Why you can apply voltage division, for example. But in this finite bridge, it's actually hard. So what do we mean by this? Let's look at this easy problem. Okay. What do you mean by this? This case is easy. This particular case is easy. The finite case, what is given in the question is relatively harder. Okay. Let's do the same thing. Okay. Notice, let's call these 2 points A, B for reference. This is A, this is B. Okay. We have V5 here. Quickly, let's look at this easy problem. Let's say this resistance is infinite, that is not connected. Okay. Easy problem. And someone tell me what is VAB, that is VA minus B. If you want the numbers, let me just give this. This voltage is 100. This resistance is, I suppose, 30, 45. We have 60 under 30. Can you tell me what is VAB? Notice the currents here are 0. It's easy problem. Specifically, it's not connected. This R bridge is infinite, right? Easy problem. That is, bridge resistance is infinite. Bridge resistance is infinite. In this case, can you tell me VAB equals VA minus VB? Okay. VA is a fraction of 100. It happens to be 45 by 75. And VB is a fraction of 100. It happens to be 30. And this happens to be, I'm considering a alternate problem. How we consider as infinite, it is an easy problem. I'm not solving this problem right now. I'm solving an easier version. We'll solve this and then we'll go back to the hard problem. How we consider as infinite, let's say they give you this question, they ask you to find VS. I'm just telling you this is easy. What I have done here is I have applied voltage division. Why can I do that? Notice the current, I know bridge resistance is infinite, so current is here. And can you tell me what this value is? I suppose this is correct. 26.674. Okay, how can you find as a bridge finite or infinite? You look at the values, right? For example, in this question, it's not connected by a wire. So what is the resistance between them? It's infinite. No current can flow through it, right? In this question, this is given, right? R3 is 90 ohms. R3 is given to be a finite value, 90 ohms. If R3 is infinite, we are looking at this question. This is, notice, R3 equals infinite. Okay, so this is 26.67, and the current here is it. And IAB, I bridge is 0. Is it labeled here? Notice. IAB equals I bridge. You know both the currents and you know, okay. See, R3 is infinite, implies IAB equals I bridge equals 0. In fact, which is why we kind of applied this voltage division, right? We could apply this. Take this, the given problem. Can you apply voltage division? So label the same points. Call this A. Call this B. Can you find VAB? We find the notice. To find the current in R3, the current flowing through the resistor R3, we have to find VAB because current, you know the resistance, you find the voltage, you can find the current, right? Even here, the question boils down to what is VAB, and this is what I refer to as the hard problem. The bridge resistance is finite, so this is hard problem. How do you know that? Let me say R3 is, R3 in this case is D. We cannot apply voltage division as we did here. So what do we do? First notice, IAB is VAB by RAB, R3. Okay, so now our question is, what is VAB? From what we have learned so far, can someone say how to solve this? Find VAB, we are done, but it's not as straightforward as if R3 is infinite. What do you do? And let me also tell you one more thing. This is a problem that we can solve with what we have learned so far, with the tools that we have learned so far in circuits. All source transformations, all series parallel, one variable the source transformation series parallel, we can kind of do this. But can someone clearly and concisely state how to find this VAB, or in fact how to solve this problem? So if you had to point this out, notice IAB equals VAB by R3. But now the question is, what is VAB? This is related. You can't apply voltage division. Come on, with whatever we have learned. So what do we do? So what are the techniques that we have learned so far? 26.67 divided by 90. No, you derive 26.67 without that resistance. If you put that resistance, the VAB will be different. No? Here it's a fair guess. Here VAB, you can find it because you can apply current is 0, voltage is 26.97, 26.67. But the moment you put a resistor there, current need not be 0. We already saw this is unbalanced. Current is not 0. In fact, that's what they are asking you for. Hopefully one of these 4 values. VAB doesn't remain the same. So what to do? Quick answer. You do source transformation. You do equivalent. In fact, you do a circuit transformation at R3 connected at 2 points A and B. You have to find an equivalent circuit. You have to do Thevenin equivalent. Right? Rest of the circuit. AB is here. You have point A, point B. Rest of the circuit that you approximate, it's Thevenin. So you have VT, you have RT, and this remains by definition. This remains. So now the question is, how do you go from this to this? You go from this to this. You already know the 2 things. Find VThevenin, you have to do certain things. Find RThevenin, you have to do certain things. To find VThevenin, move all sources I mean, Thevenin is just this in the original circuit, open circuit voltage across the load. Thevenin, remove all the sources, find equivalent resistance. To find Thevenin, let's find Thevenin. Remove the load in the circuit. Technically, what I am doing is I am shorting the source. I'm shorting this. I'm removing the source. Short. And what I have to do is to find R equivalent across these 2 points. I have point A, I have point B. So now I have made AB open circuit. By definition, I'm removing the load. For the rest of the circuit, so remove the sources, find R2, 4. So this is R equivalent below. That is, we'll come to that in a moment. Okay. Now we have to find R Thevenin, you have to find V Thevenin. The moment you have it, it's a simple circuit. No, you can actually find the current. No big deal. You can find the current through R. Step 1, you need this. Step 2, you also need V Thevenin. How do you find V Thevenin? This is what I have done. Remove the load, right? Voltage across the load terminals. Notice this by definition, AB here is essentially V Thevenin. All I have done is remove the load, find the voltage across the 2 load terminals. Is by definition V Thevenin. So to find, what I have done is to find V Thevenin. We did this. We already did this. See? We already found the V Thevenin of the circuit. It's a simpler problem. So you remove the load, or the load resistance is infinite. What is the voltage across the 2 terminals? You can find. So let me mark that. Your V Thevenin is, in fact, let's get a fresh page. V Thevenin, we found this to be 26.6. You have to find R. How do you find R Thevenin? Can someone again concisely tell me R Thevenin is essentially, there is a equivalent resistance here between A to B. Is this series parallel in terms of R1, R2, R4, R5? Okay, you are telling me numerical value, but some of them might be lagging. And what I need is rather that in terms of series parallel, can you tell me, is it a series parallel thing? In fact, let me give you 2 options, okay? Option 1, option 2. We have R1 parallel R2 in series with R4 parallel R5. Another option is R1 parallel R4 plus R2 parallel R5. I'm trying to write down R equivalent here. Tanasi is option 2. Is there anyone who thinks it's option 1, or can someone explain why option 2? Not this option, it is this option. The simplest way to look at that again is essentially the same point connected by a wire. It's all the same point connected by a wire. It's all the same point connected by a wire. You have A, you have B, and then you have voltage source is shorted. This is shorted. That's the procedure for it. Now you could call this point C. I have point A, okay. I have point B, and then I have point C. Point A, I have point B. What I notice is from A, resistance going to R1 going to point C, R4 going to point C. Is all the same point. Why is that the case? It's the same wire, no resistance. Equipotential. From A, there are 2 resistance going to point C. We have one of them is R1, another one is R4. B, there are 2 resistance going to point C. So C to B, there are 2 resistances. These are R2 and R5. Notice, so R1 is parallel to R4. That is in series with R2 plus R5. Can we do R1 plus R2 parallel R4? No, R2 is not parallel to R4 because R4 is going from A to C. From B to C. A and B are 2 different points. No, you cannot do that. 4 is between A and C. R2 is between B and C. You cannot do that. General fair question, but you cannot do that. There is like only one correct equivalent thing here, and that is the option 2 that I gave. But explanation makes sense because this is a place where students get slightly confused, and that is understandable. That's why I try to somewhat color code and explain. Then did you get it?
Yes, sir.
Get that very well. Fine. So okay, the others. No. Can you tell me what this R Thevenin is? I think you can turn off your mic whenever you want to use it. You could turn it off. Hey, what is this R1 parallel R4? That is simple. No, R1 R3. Do you want the values? Fine. Let me write them here. What we want is R1 parallel R4 plus R2 plus R5. This values happens to be R2 is 60, R3, finite resistance, bridge resistance that we know fine. This is 60, R4 is 45, and this is 30. So we have 30 parallel with 45, 60 parallel with 30. How much is this? For everyone's sake, I will also write it down, but I'll erase it. Okay, this 30 parallel 45 plus 60 parallel. Give me one number. 30 parallel 45 is 30 into 45 by 75. Make 30 plus 45. That is 75. 60 parallel 30 is 60 into 30 by 60 plus 30. That is 90. R1, R2. So Kirtana, I think long back answered 38. Fine. Others, Kirtana went to the next step. So current is 0.208. Suppose that is correct. Okay, 0.2. What do you erase this? This happens to be 38 ohms. We need this number, 38 ohms. Okay. And now if we go complete the problem, so we know Thevenin, Thevenin, it's a simple one loop circuit. We can answer that, right? This is 38 ohms. This we know as R3 happens to be how much? I suppose it's 60. Right? Make sure that it's 60. R3 is 90. 90. And now there is point A, point B, across which we found B. Now there is a load that the rest of the circuit is simplified. What we want is what is the current through this? A parallel, very, very simple. I is just P Thevenin, right? These two are in series. R Thevenin plus R3. Notice, long time back, someone asked me, sir, is it 26.61 by 90? Notice, we missed this R Thevenin factor. This is 26.67 by, you have R Thevenin 38 plus 90. 38 plus 90, right? This is how you deal with this finite bridge resistance. What is the thing? So do source transformation or find the Thevenin equivalent, then you have one loop and so on. Okay, this happens to be, I suppose, 0.208 amps, and this is your answer. And you could go here. This is your answer. Option B. That is option B. This is amps. This is not A, B, option A, option A. This is option B, that is 0.28 amps. So that completes the next important thing that I wanted to discuss about Wheatstone bridges. Let me recap. See, to find maximum power transfer, you have to do this Thevenin and Thevenin business. This bridge resistance is finite. That is, if a current can flow through it, again you have to do a Thevenin and Thevenin transformation. No. Current is not negligible, right? Zero is, current being zero is different from current is negligible, right? Even this is like 0.02 is like finite. So technically, so the infinite is essentially zero current. Close to zero, no. In fact, close to zero matters. See, the resistance is kind of finite. The current is too small. But that would really depend on how balanced or imbalanced the bridges are. In fact, the given scenario, they have made a diagonal change, right? Let's say all three are 30, 30, 30, 30. They have increased this side by 45. They have increased this side by 60. They have created an imbalance, right? 30 plus 15 here, 30 plus 30 there. There is an imbalance. Because of which, there is a current flow. So, notice they are creating an imbalance at diagonally opposite sides, right? So that there is imbalance. So, negligible and zero are different. Okay, let us, and the direction of the current, plus 0.21, right? The AB we marked it, we have to hold on to that. Actually, these two resistors are telling whether VA is higher or lower compared to VB. In this case, VA is higher than VB. So, direction of flow of current, I suppose that is shown. Okay, one of the details we have to be careful about is the current flowing through resistor R3. Okay, they have shown a direction there. They have put an arrow from A to B, current is flowing. If they have given a different direction, the answer is different. Okay, be careful about the arrow because we know this VA is higher than VB or the Thevenin voltage, right? VA is positive. VA is at a higher voltage. Be careful about that detail also. Okay, to summarize, we have already done this. Last time we did lots of Thevenin to Norton conversions, but we also learned circuit to Thevenin conversion, right? This is useful both in case of the maximum power transfer theorem. Questions like this one where you'll have to replace a circuit like this here, or it's also useful in case of a finite bridge, which, finite resistance, Wheatstone. Infinite resistance is fairly easy to answer. In fact, it shows up as a sub-problem. This is fairly easy. And in fact, it shows up while finding the finite bridge is fairly, relatively harder. It involves you have to find R Thevenin, you have to find V Thevenin. Once you do that, that's it. You can easily get it. Right? Be careful. Students make a mistake while finding R Thevenin because they typically write option 1. Okay? You have to see where the equipotential points are. Connected equipotential points will behave as 1 point. All the blue thing behaves as 1 point. It's all resistances. Those are wires. Okay, this compared to this other, isn't there a negligible potential drop in the wires? Compared to this, the changes are happening in 6th or 7th decimal place. Right here, that is the difference. When is it negligible? It would be a fair question, sir. Wires are having, at the end of the day, has some finite resistance, right? There is current through the wire. There is a potential drop. That is happening 6th or 7th decimal place. Now, what I have here is, let's summarize. Okay, max power transfer. We have infinite bridge resistance. Let's kind of write it in a slightly different order. You have 2 bridges. You have finite bridge resistance stone bridge, and then you have infinite bridge resistance Wheatstone bridge. And you would, for both this, you will have to do circuit to Thevenin form, both that. And this is a relatively harder. This is the easy version. And often this is a sub-problem and this conversion. Okay, now comes, so we are done with circuits that have resistance. Okay. These are what I refer to as, these are typically 0th order. Only resistances. Changes are instantaneous. You could also always, is due to then RC or LR. And then we have R, L, C. Okay, so this is what we have done so far. Only resistances. What we are going to look at now is this, and what this is referred to as typically, instantaneous, right? This is referred to as 0th order. This is referred to as 0th order. That is instantaneous. Okay, 0th order circuit. This is what we have done. This is known as first order circuit. And then we have second order. Typically, when you have RLC, you have a second order. For these 2 things, okay, you can do, if you understand, there is something called impedance. This was there in the short playlist that I did. There is this playlist I gave you a couple of weeks back. And right? So, if you follow that playlist, whatever you need to know here, that one major trick is this impedance. And with that, we could, notice whatever we did till here with resistances, could do all of that with impedances. So if you understand how to work with impedances, okay, so whatever so far you could do with a 0th order circuit, that is circuits involving only resistances, you can apply all of that to first and second order circuits. So impedance plays a role of resistances in a 0th order circuit. Is there a max power transfer theorem? Yes. Can you start analyzing Wheatstone bridge? Yes. Okay. Can you do voltage division, current division? Yes. Okay. Can you do equivalent resistances, equivalent impedances? Yes. Series parallel? Yes. Delta, star delta? Yes. Here we have learned so far. Okay. We could actually use the same thing. That is, if you are following till now, okay, and if you understand this one thing called impedances, you could actually solve most of the first order, second order problems. And that is kind of discussed in the playlist that I shared. Okay, if I remember correct, this playlist is also available publicly. Okay, if you want to learn this, but I think this one playlist, short playlist, kind of available publicly. So I'll put a reminder, but I'll see whatever I had rehash right now. I'll do that and we'll proceed. First, let's look at the first question or concept that shows. Okay, the following circuit, the switch S is open for t less than 0, closed for t greater than or equal to 0. What is the steady state voltage across the capacitor when the switch is closed? Okay, suddenly now open, closes. What you have initially is this transient circuits, okay? Steady states and transients. Let me tell you the basic theory relevant to this. Solve, write it for an inductor and then for a capacitor. How do I split this? First do for a capacitor. We have in fact, we'll even come to the inductor after finishing this. What is the relationship between voltage and current in a capacitor? Let's wait for even the inductor. How is voltage and current related? If you want even fact, kind of resistances, right? This V is IR. What is the relation for a? What is the equivalent relation? I mean, how is in a capacitor? How is voltage and current related? Voltage and current. How is that related for a capacitor? I is C dV by dt. You can use Q as CV. Differentiate both sides. You can arrive at this. dQ by dt is current I. Q is charge. Right? Charge in a capacitor is CV. So if you differentiate that, you get this. Current and voltage are related. Again, this is something all of you have seen. I is C dV by dt. Notice this is instantaneous. This is what I refer to as zeroth order. Instantaneous. This is a differential equation. This is transient, time dependent. You have voltage, current as a function of time. There is no time dependency here. Whatever is the voltage, instantaneously, the current is proportional to that, right? But here is VI. This is, I square R. Energy in a capacitor, does anyone know? Energy in a capacitor? Half CV square. CV square. CV square. This V could be a function of time. Okay. So energy at any given instant can be a function of time. This is half CV square. And let's also do one more thing. Okay. I may have to extend the notes here. But let's kind of extend note, continue it in this page. Now, see, there is something called Laplace transform. You can convert differential equations into algebraic equations, but it's a transform. The way you look at it, transforms, typically you are converting a hard problem into an easy problem. You are moving from an inconvenient coordinate system to a convenient coordinate system. Simply hard to easy problem. So notice, take Laplace transform here. How are these things later? You will get I of S here. As a Laplace transform of a derivative, C is a constant. You don't have to worry about it. Does anyone know the Laplace transform of derivative? What is dx by dt? What is the Laplace transform of that? Again, I am not asking something like way too difficult. Some of you, one or two of you might know. Yeah, SV, right? So you have SV, C that remains. And typically minus the initial condition but we'll not worry about it. Okay? It is typically minus initial. Let's not worry about this. Let's not complicate it. This is SVs or SCV. No, multiplication of this. Notice you could also write it over here. V of S is I of S into R. There is a very easy way to go from, this Laplace transform to one version of Fourier transform. All you have to do is, S equals A omega. And technically notice, this is, write it in the same order as we have that equation. We have C and then we have S, V of S. What I get is, this side is J omega, S is J omega into C. Into V, some function of J omega. Essentially, it's a function of omega. J is a constant. So I'm going to write it as omega. Function of J omega. J is a constant. So I write it as the function of omega. You could also do the same thing here. Notice what I have here is I of omega happens to be. You could write it I of J omega, but that's just a notation. I of J omega, but it's just notation. Typically, we write this as I. It's a function of omega. J is a constant, so you don't explicitly write. You also need some space, so kind of let me slightly erase this. Let's not give it so much space. Yes, this I substitute. This is J omega. This is J omega into C into V of omega. If we do the same thing here, I have V of omega as R into I of omega. Just that, see, This will be functions of S. Only if V and I are functions of time by definition in the Laplace transform. Okay. V and I are not functions of time here. So V of S and I of S essentially are constants. V of omega, I of omega are essentially also constants. But the thing is, definition of impedance is this. Notice here R equals V of omega by I of omega. This is what we refer to as the impedance, ratio of voltage as a function of frequency to current as a function of frequency. What is omega? I'll give you more relatable numbers. Okay, for right now, this is a frequency. Notice, this is by definition impedance. It's not. So our resistance for a capacitor and inductor, the name for that is actually impedance. Resistance like thing. Just that we need to account for few other things. Things can be functions of time or functions of frequency. Still, the ratio of voltage to current is impedance. Impedance. See, so now it came to a problem. What is impedance of a capacitor? What is V of omega by I of omega here? This. Notice, by definition, this is V of omega by I of omega. That happens to be 1 by J omega. Let me also slightly conveniently write it this way. Impedance by definition is V of omega by I of omega. That happens to be. So far so good. ISC dV by dt, all of you know. Energy in a capacitor is half CV square, all of you know. Basic Laplace transform went from here to here. Okay, basic Laplace transform. And then it so happens in the Laplace transform, if you put S is j omega, you get frequency dependence. There is no, you can also call that as Fourier transform. And impedance by definition is just the ratio of the function of V is a function of omega, I is a function of omega. That is, V is a function of frequency, I is a function of frequency. The ratio of the two functions is impedance. Like what? Okay, the ratio of voltage and current in resistor, right? That's an impedance of a resistor, for example. Most of the things that you need, I have made it as simple as possible. If you have questions, I try to show analogy with the resistance that we know very well. If you have a question, raise it, right? If we find space to write, this is time dependent, that is obvious. So I'm going to kind of erase that. This implies something. Capacitor doesn't like something. Can someone spot that? ISC dV by dt. It says capacitor is hesitant to do something. Not just hesitant. In fact, yeah, it is kind of hesitant to do something. Can someone look at that equation? Tell me capacitor doesn't like to do something. Okay. This question is harder. Let me make it slightly easier. This doesn't like sudden change in V. Suddenly changes. dV by dt is infinite. Current is infinite. That is not possible in a realistic circuit. Either it's shorting or the wires are melting, something like that happens, circuit gets damaged typically. Capacitor doesn't like, okay, sudden change in voltage. Right? If dV by dt is suddenly changes, it's infinite. I is infinite. Not possible. Just one more thing. Here, resistance is a constant. Doesn't depend on frequency, but this depends on frequency. Notice, in fact, let me write this in gray. As omega tends to 0, Z tends to infinite. Omega tending to 0, signals are not oscillating. Frequency oscillation, things are not oscillating at all. The name we have for that is at DC, capacitor impedance, capacitor resistance is infinite. Capacitance open circuits. In fact, most of the things that you want to know for RC circuit about a capacitor, I have it here as far as gate exam is concerned. Notice at DC, again, this is something that we have. Capacitance open circuits. Recall, okay? ISC dV by dt, all of you know. This says voltage cannot suddenly change. If it does, current is infinite. There is a problem in a physical circuit. Energy is half CV square. Laplace transform or otherwise, you recognize ratio of voltage to current is a function of frequency that happens to be 1 by j omega c. All of us know that. This is referred to as impedance. And looking at the impedance, you can see at DC, that is omega equal to 0, capacitance open circuits. opens up. There are no current flows. In fact, you can also kind of write this as that is at DC capacitance open. We have this common analogy for this, that is, if you put this, right, DC gets blocked, right? And then we have this, just a mnemonic, AC current flows through. What is happening is, notice at omega equal to 0, this is DC omega equals 0, Z is infinite, here Z is 1, 2, 3. This also you can afford to forget. I know this Laplace transform, Fourier transform, fine. But impedance is 1 by j omega c. You know those 4 things and the consequences of that, you could answer most of the gate questions. Let's look at one. The following circuit. Switch S is open for t less than 0. This is open. And closed for t greater than or equal to 0. What is the steady state voltage across the capacitor when the switch is closed? Concisely, someone tell me how to do this. Please tell me which of the things that I mentioned here we are going to use. This has been open, fine. Now what you do is you close this. Let's say the switch is closed. At steady state, they are saying after a long time. This is after a long, things are not changing. After a long time, how should this capacitor behave? Okay, fine. Even, if you say, there are again slightly too many things to connect here. Some of the box thing, let's say you kind of remember, okay? I know a couple of things. This is DC source. I know that Z is 1 by j omega c, okay? At DC, capacitor opens. Capacitor opens. Sometimes it takes, it is initially charging. That is certainly after a long time, certainly open. This is what, at DC, capacitor opens. That is notice. Here, if you have to see as omega tending to 0, this denominator goes to 0, numerator goes to infinity. We have at DC and opens after long. Resistance become infinite. So what happens to this capacitor? At least now can someone answer? Hope no one has issue understanding what opens means, right? Resistance become infinite. They are no more connected. After a long time, this capacitor behaves, this point almost opens up. If I have to even draw that, long time, that is steady state, the circuit that you have here is open. This is a circuit that you have. Can you tell me the voltage across this capacitor that happens to be, let's label the points B. The capacitor opens, doesn't allow any current. So I have removed from it. Voltage across the capacitor is essentially voltage across AB in the circuit. Fairly easy to say. Now, this is the resistance problem. This is 10, this is 3, this is 7. Can we tell what is AB here? Is also there is closed. If you cooperate, we can. I almost give you, the answer. We are back to a simple resistance circuit. We can answer it. We just need BAB. At least tell me where are the issues. You're not following. I'm confused with this detail. I'm not following this detail. What they are asking is, let me also know what is the steady state voltage across the capacitor when the switch is closed. So when the switch is closed, the steady state that is after a long time. This is the circuit that we have. Capacitor is not there. It opened up. Its resistance became infinite. Okay, so some of you are doing fine. So what is the voltage across the capacitor? Essentially, what is VAB? That is what right now we want. Okay? What we want right now is VAB. In fact, let's kind of slightly write it different colors. Voltage across the capacitor is essentially V7. Great. This is 7 volts. How? Notice. Hey, this is open. No current goes here. So I is 0. IR is 0. There is no potential drop across 10 ohm. It's all the same point. IR is 0. Potential drop is 0. For that reason, this point also behaves like A. Why? Current here is 0. I equals 0. There is no current. There is no potential drop. That is essentially 1 point. So after a long time, you have this circuit. Okay. Here, no potential drop. No V drop. No V drop. So this point is same as this point. It should be 3. How is it 3? I is 0. You can apply voltage division. 10, it's a fraction of 10. That fraction is 7 by 7 plus 3 into 10. Right? Fraction of 10. No. There is a drop, 3 volt drop across the 3 kilo ohm resistor. 7 volt drop across 7 ohm resistor. Voltage across A to B is same as voltage across A to B. Yeah, that happens to be 7 by 7 plus 3 into 10. There you got your answer. 7 by 7 plus 3. No, the fraction of that. Let me write it here. So the answer 7 volt. That's it. If V is IR, larger the resistor, larger the voltage drop. Right. I is D by R. Larger the resistor, smaller the current. So now larger the other resistance, right? More the current through this one. Kind of voltage and current division. That's why the things change. Okay, there is a simple thing. V is IR, larger the resistance, larger is the voltage drop. So you can easily say, hey, 3 ohm resistor, 3, 0.3 fraction. Here 0.7 fraction. So let me take a step back and see what we did. Actually, I have space this side or that side unknown that because I was running short of space. Using some of the properties of a capacitor, which property? Essentially, if you know the impedance of a capacitor, you can do this. Impedance of a capacitor 1 by j omega c. It doesn't allow DC at steady state. There can be transients. Capacitor can slowly charge up, but after charging up, it won't allow any current to pass. That is why they say steady state after a long time. Okay. So at DC, capacitor opens up. What happened in the point? The circuit with the capacitor became a circuit with only resistors, which we know this is like home turf. We know how to how to handle that problem. So one simple thing, circuit becomes all of a sudden familiar circuit. Capacitor, resistance capacitor circuit, but the question, one minor detail, hey, is this a resistance circuit? For what they are asking. Many other things in the circuit, but for what they are asking, this is resistor circuit. How to solve. And we made some, this Z is J omega C, this is going to, this is one thing that you really need. It's going to show up again and again. Even if is a capacitor opens or inductor opens, there is a confusion, you can actually quickly deduce that. Hey, what is omega? I'll show it to you. I'll kind of demonstrate or I'll give you simple numbers and illustrative things when we look at AC circuits. Okay, we are still in DC. Now comes the point. I told you how to solve this question, but this year in GATE exam, they may not ask you the same concept, but not voltage across a capacitor at steady state. They can ask you few other things. Towards that, I should also tell you few more things. Erase the given question. I'm going to consider other question. We answered the given question. But what are some related things they can ask? I'm going to answer that. And for that, we need to know what is the voltage is. Voltage is a function of time. We have P capacitor, and then we have voltage capacitor. Interesting. Now this is a function of how should this look? In fact, so we have situation starting from t less than 0, switch is open and all that. T equals 0. After a long time, let's say this goes here. So the switch is open before t equal to 0. There is no current through the capacitor. Current is 0. Nothing is going in. It's open. Okay, this is a dangling part of the network. It's not closed. Switch is open less than t equal to 0. So the voltage in the capacitor across the capacitor is 0. And at t equal to 0, you all of a sudden close the switch. You complete the circuit. What should happen? Can someone very, very in simple English say what should happen? We have this scenario where t less than 0, switch is open. Switch is open. At t equal to 0, we close the switch and keep it that way. What should happen to the voltage across the capacitor? Simple English. Again, this is something that charging, decharging of a capacitor, you're actually very much used to. And when you're learning something, initially you learn a lot. And after you proceed to something, the amount of things that you learn is smaller and gets smaller and smaller. There is some sort of saturation. And we also, I think, we give some names for it, right? I had a very important special class, the most important topic in GATE biomedical exam. In fact, the most important topic in most GATE exams, okay? Exponential decay saturation. Can someone put this into simple English? How should this voltage across a capacitor change as a function of time in two or three words? Eventually, let's also see what is happening. Eventually, it goes to 7. Eventually, it is at 7. Exponential decay, but as you close the switch, all of a sudden you're applying a voltage. Okay, it saturates at 7, and there is like exponential saturation. Initially, there is a lot of change, then change becomes smaller and smaller and smaller. There's just 1 minus decay, okay? 1 minus exponential decay, saturation. I also want this bit and get it somewhat correct. So there is in shooting, sometimes there is, there are actually two types of shooting. One is called normal shooting. You try to aim, shoot, look at the things and aim, shoot and all that. The other one is your gun is not between your target and your eyesight. You are holding the gun at hip position and you are shooting. Like Keanu Reeves in, what is this movie? Latest series of 4 movies, and then there is one more movie coming up. Keanu Reeves, right? There is this, ballerina movie coming up based on, spin-off from that original thing. Does anyone know this movie that I'm talking about? What was the latest Keanu Reeves movie that was a very, very big hit? John Wick. Has anyone seen John Wick? Notice John Wick, if you notice the entire movie, they show his expert level by actually a very, very simple thing. He doesn't put the gun between his eyesight and eyes and the target. He'll keep the gun at position and shoot. Okay. So typically most people will try to aim and shoot, right? But you could also aim without getting the gun in the line of eyesight. That is known as instinctive shooting. So like that, I have a similar problem. I'm not yet an expert, but I have this Wacom tablet. It is oriented in some way. So if you have to draw a straight line, okay, if I try to look at the tablet and draw, it goes wrong. Okay, I'm trying to get used to directly, looking at the screen and draw, not get this tablet and draw. And also this Wacom tablet position keeps on changing. So I have this simple straight line sometimes that is not so knows. I have some issues drawing. Reasonably looking exponential saturation. Fine, I'm not going to bother. That is not exponential saturation. There you go. And I'm going to cheat a bit. It will change the saturation value. K value is going like this. I suppose that is far easier. Yeah. Notice you suddenly apply a voltage at t equal to 0. Voltage across the capacitor doesn't suddenly change. Voltage suddenly changes, current becomes infinity. Voltage only gradually changes. So if you look at this point, 1, Vc t minus equals 0. 2, Vc, that is, it's not t minus, sorry, 0 minus. Slightly below 0, voltage is 0. Slightly above 0, voltage is still 0. Why? Cannot suddenly change. No sudden change in V. dV by dt is 0 and then current is infinite. The problem that we solved here, this is steady state. After a long time, what happens? Capacitor is fully open. When will that happen? It is totally exhausted. It is totally saturated. It cannot let any more. It cannot hold on to any more charge. It cannot, there is no dq by dt. There is no current. That's it. If the capacitor is eating, it is like rim full. It's like mouth full. Everything is like totally filled, right? Not stomach full. Stomach, esophagus, mouth full. Capacitor cannot eat anymore. There is no space for charge in the capacitor. No current. Nothing can go inside anymore, right? That is steady state. Capacitor is saturated. So the thing is, I was not actually feeling, I was held up with a couple of issues, and I couldn't think the way I usually do for, a couple of days. Only after taking the class, okay, for some reason I enjoyed so much that this preferred mode of thinking and, thinking actually opens up. It took me actually 2 days. I kind of struggled with the very blocked writer's block or a teacher's block. Not a teacher's block, but sort of mental block. Now, as I'm taking this class, it's kind of, I'm getting relaxed. Some of you might be getting tired, but actually, I like the classes that so much that I kind of get relaxed. I get more relaxed as the class proceeds. Okay. The question that they asked, hey, what is the voltage of the capacitor at V? What else can they ask? They can ask you what is the voltage at 1, what is the voltage at 2, right? What is the voltage at 0 minus, what is the voltage at 0 plus? They can ask you for the voltage. What else can they ask? Come on, quickly. There is a fourth thing that they can ask. So all these are all possible questions they can ask with the same thing. This is essentially VC of infinity. We solve this question. Question 4. Find time constant. Okay. That is, we have space. Actually, that's a very good answer, Yetana. Okay. But before we go to that, hey, why ask voltage at 0, this at 0? Right? Energy of the capacitor at 0 minus energy of the capacitor at 0 plus energy of the capacitor at steady state. They can ask you this. So far, fairly easy. Hey, the capacitor opens up, man. It doesn't have any more room for charge. No current. It saturates. It's a simple resistance problem. We solved it. What is happening all along? It is gradually, exponentially saturating to that steady state value. All these questions we can answer. If you know the voltage, you know half CV square. You can find the energies. You can find the energies. We can find energies. So what is the fifth thing they can ask? Sir, in 4 itself, you put EC0 minus, EC0 plus, EC infinity. They can also ask you one more. Let's say the fifth, suddenly, you'll hold on. That's a surprise, or, climax will reveal towards the end. Exponential saturation is a very, very simple curve. There is one constant there. Time constant tau. I think Kirtana mentioned it. If you know that, you know voltage as a function of time. That happens to be the saturating voltage 1 minus e power minus t by tau. Notice t tending to infinity. This term goes to 0. E power infinity minus infinity is 0. You have V naught. T equals 0, right? This term is 1. 1 minus 1 is 0. So VC is essentially 0. At this stage, I can notice two things. VC of 0 is V naught into 1 minus 1. That is 0. And here things are continuous, equals. So at this stage, notice, we know the voltage at any time. Not at 0 and the steady state. At time 1 second, you know that. Time 5 seconds, you know that. Give me the time, I will plug into this and find what the voltage is. Give me the time, I can plug that into and find the voltage. Give me the time, or give me the voltage, I can plug it into that and find you the time. This also happens. It cannot change abruptly, so we have the initial voltage. If you know that, if you know voltage as a function of time, you know energy as a function of time. Substitute the voltage at that time. You know the energy, you know voltage and energy at any time. You know voltage, energy at any. So the last is, sir, but you put this tau. What is the tau? Time constant. Tau is RC for the RC circuit. Sir, there is more than one resistance. What do I do at that point? And then see. So for the rest of the circuit, you can find the Thevenin resistance and then Thevenin or the equivalent resistance typically. Okay. Depending on the problem, but or sometimes it's also or equivalent C. It can be C equivalent also, but simplify. It's RC. There are more resistances R Thevenin C. Or even in simple terms R equivalent. So if you know the time constant, you know this whole function, you know 2 months of electrical circuits. Okay, done. 8:30 will go till 9, okay. Notice I left a gap for inductor, right? We'll fill up this gap. Perhaps let's read this PYQ and just point B. If this one, which of the 7 couple of simple questions that I mentioned, which of the questions are they asking? Just point that out and we'll wind up. We'll come back tomorrow and then we'll continue with the discussion. And things are functions of time right now. We made one use at DC steady state. Okay, what is it? It opens up. That is the only omega that we used. We had to come back and use 1 by j omega c. But I think by the time we do that, we will also get to second order circuits. You need phasors and impedance as much as possible. I'll try to simplify and solve this. In fact, it so happens that most of the PYQs are actually very, very, very easy if you just understand that impedance. If you know complex number, if you can do complex algebra, you are actually done with this. Complex number algebra, you're actually done with this. Let's recap, and then we go till let's just, on the way, I'm going to recap. Let's, ask quick, simple questions. It's okay if you don't answer. I'll just move on to the next student. I'm skipping 2-3 students. I will post and make it open. Initially, I didn't see some of these names. Sarvani. I hope I'm pronouncing your names correct, okay? You could either correct me now or later on also tell me, sir, you should say my name this way. If perhaps, so Wednesday meetings, we should, hey, sir, my name is this. You are actually not pronouncing it correctly, right? All of that you could do. Sarvani, so why doesn't a capacitor like sudden changes in voltage? Why doesn't it like that? Sudden changes in voltage? Simple explanation. Okay. So again, out of some privacy concerns, I'll also try to make it reasonably private. Okay. Jaya, right? Ending with E. So Jaya sir, Jay will, right? Dr. J, sir Jay. Jaya ending with E. Darshin, Janvi. Okay, anyone. Why doesn't it like sudden changes in voltage? Short 2-3 word explanation, concise explanation. Anyone? If voltage suddenly changes, what happens? So now some students are like, how can it not suddenly change? I will put a circuit with the DC voltage in the switch. Suddenly change, close the switch. If the capacitor doesn't change voltage suddenly, it will violate Kirchhoff voltage law. Some students are thinking like this, right? I will design a machine, that, that will violate first law of thermodynamics. I will design a machine that will violate second law of thermodynamics, perpetual motion machine. I will design a circuit that will violate Kirchhoff voltage law. Things like that doesn't happen. Certainly in our undergraduate linear realm, voltage suddenly changes. Slope is infinite, current is infinite. dV by dt is infinite, current is infinite. Okay. So if some of you are trying to use a mic, you could try using chat. Okay. Let's go to the next question. So energy is half C square. Most of you know that. Some Laplace transform, Fourier transform. Okay. The impedances is ratio of voltage and current, which are technically in this case, it's a constant. Technically, this is a constant. Technically, this is a constant. It's not a function of frequency. It's not a function of S. This is V by V of omega by I of omega. Voltage and current both are functions of frequency, right? In a AC circuit, there this ratio is defined as impedance. That happens to be 1 by j omega c. Most of you know that. And here you can see that if omega is 0, denominator is 0, this is essentially omega is this. Again, some of your oscillatory circuit, sinusoidals, oscillation frequency is omega. Right? Omega is the frequency of this. This is in radians per second. We'll come to that, but that is omega. If that frequency of oscillation is 0, it is not oscillating at all. It's DC. So eventually it kind of opens, right? This impedance is in. Okay, there is a mnemonic. DC capacitor doesn't allow. There is a roadblock. AC, this will like go zigzag and pass through the capacitor. For the gate PYQ, it kind of capacitor opened up. Simple resistance circuit. VAB is 7 volts. That is voltage across the capacitor. We looked at the steady state. It remains 0. Doesn't suddenly change, but only gradually change. Specifically, exponentially saturate to 7 volts. So they can ask you any of these voltages, any of these energies. And if you want to describe this transience, you need the time constant tau. Time constant here is RC plus RC. The rate at which things are changing depends on this time constant. Okay, let's head back here. I finished that monologue. How is voltage and current related in an inductor? I use C dV by dt. Inductor is essentially like a solenoid. Current in the solenoid changes, it kind of generates a electric field and associated voltage potential, right? Potential across the terminals. Great, thank you. So this is fairly simple. Let's write clean. V is L inductance, self-inductance, di by dt. And this says doesn't like sudden changes in time. I write it. Can someone complete it? Sudden CHANGES in Hugo. Got it. So most of you actually knew the answer, but somehow couldn't answer, right? In current, if current suddenly changes, dA by dt is infinite, voltage is infinite. In a physical circuit, infinite potential drop. No, potential is infinite at one place. Something is burning or something is fishy, something in probably the fish is burning, okay, in that case. So doesn't like sudden changes in current. Energy, most of you know. Again, energy is a function of time. So, you all of you, any of you is welcome to fill it up before I, complete writing this, okay? My interface is slightly bad. ENERGY technically this is a function of time. Notice voltage, currents are functions of time. It's a differential equation. This happens to be half. There is also half here. Actually, I square. The Laplace transform, this is that and all that. We'll kind of shade it out. Of S is SL. Derivative is with current, right? So SL I of S. If you substitute in S is sigma plus j omega, that is if you don't consider any transients, right? That is if you substitute S is j omega, from Laplace transform you get to Fourier transform. You have, again, let's grade out this way, right? I have V of omega is j omega A, j omega L. I have seen it somewhere, right? Some of you are writing Z is j omega L. Yeah, I guessed it. Great. Z is j omega L. Omega is in denominator for a capacitor. Omega is in numerator. There is no denominator, but fairly simple, right? Hey, J, what is that J? Dr. J. You have to, you didn't say what is a J. You said J is a constant. J is this complex number. Technically I have to write it somewhere where I am defining it. J by definition is square root of minus 1. What if such an entity exists, right? So what if scenario? Like Avengers, what if this exists? Then properties actually are so useful in modeling many physical systems. Medical properties actually so useful to model or describe many physical phenomena that have come across. So that is the J. I also put it up. Let's not confuse it with that initial conditions, or let's put it slightly offset, square root of minus 1. And then here, what happens? As omega tends to 0, Z tends to 0. Can someone put this in simple English? See, there Z was infinity. This is Z. Omega tends to 0. Your Z tends to 0. Simple English, what does it mean? Impedance. Resistance is 0. It does the opposite of open. At DC, inductor shorts. Technically, I know I should also written one more thing, but at this stage you could both finish this. As omega tending to infinity scenario, perhaps is not what this is not all that interesting. Omega frequency tending to infinity is like, no, this is not a shorts immediately, punctually. That is steady state after a long time. It is fairly basic. Okay, let's not kind of warm down. Let's just see what the gate question in the circuit given below. Vs, let's zoom this. Vs is 50 volt. Let the circuit reach steady state for SPDT switch at position 1. Once the circuit is switched to position 2, same thing, switch was this way, switches this way. Energy dissipated in the resistors. Can someone describe what happens at position 1, what happens at position 2? Then we'll think about energy dissipated in the resistor. Position 1, it's there for a long time. It is at steady state. Okay, at position 1, when switch is at 1, inductor shorts at steady state. Why? Omega tending to 0. This is a DC circuit. Omega tending to 0. Z tends to 0. It shorts. Great. Hey, the simple resistance circuit. I know the inductor is kind of hidden here. Shorted. I can find the current. If I know the current at position 1 in steady state, I know the energy of that inductor. This is, let's make this look like a resistor. Some of you there is an ECG signal going on. This is position 2. What happens? LR circuit. Hey, no. Position 2, there is no this and all. Let's say inductor. It's a LR circuit. But should we do things as a function of time and all that? No. What they want is energy dissipated in the resistor. And once you find the current, you can write down the answer in one line. Finding the current is one line. Once you find the current, you can actually find the energy dissipated in the resistor. Total energy dissipated in the resistor. Right? You can write that in one line. How? In fact, we didn't discuss. I didn't put that at all here. But that's fine. There is 2 words for that. Find it out before we kind of restart this. Okay, I'll recap thing and then we'll solve this. So where we are stopping at is finding the steady state current is fairly easy. Once you know that given answer is, you can write down the answer. Answer is 1. I is 4. 50 by inductor shorted. How is 4? 2. 50 by 25 is 2. So this is I is 2. Okay, I is 2. The initial energy stored in this inductor. Okay, notice current cannot suddenly change. It can only gradually change. All of that is eventually dissipated. That energy is dissipated in the resistor, right? But what is initially stored, what was the initial content of the lunchbox, eventually get slowly eaten up, right? So initial energy content of the lunchbox or the inductor here is half Li square. That eventually gets eaten up or dissipated by the resistors. You can also write that in. Yeah, you wrote it down. You can calculate that. In fact, we can finish this, but we can redo this tomorrow morning. What is the number that you're getting? Half. Yeah, can we journalist like almost close to this? I have to do that. How much is the inductance here? 0.1 Henry. A Henry, Farad, Henry and Farad. SI units, okay? As far as you stick to Henry, Farad, all your calculations are good, which anyways, when I introduce frequency and all that, I'll make this point again. Perhaps, oh, great, we have an empty slide. I'll put this units here, okay? Henry, Farad and all that. So the answer here is 0.5, that is half, into inductor is 0.1 Henry into I square. I square is 2. This is the energy that is what 0 joules and again an energy. This is eventually this. That's the answer. Okay, explain it in more detail tomorrow's class. Tomorrow's class we'll also finish most of the tomorrow's class we'll finish electrical circuits. Okay, you need impedance. I will also try to. I cannot explain complex number algebra tomorrow. If you can do basic complex algebra, I can actually finish all of this. On the playlist, biomedical signal processing, biomedical filters, short playlist, okay, 5-minute videos, kind of starts from scratch. How do you add complex numbers, divide complex numbers, multiply complex numbers? How do you do this polar representation, normal representation? Does all of that? How do you find the amplitude? How do you find the phase? Right? And kind of takes you to a reasonable, whatever you need to handle gate problems, it kind of teaches you that. Okay? That is one. If you have that, we can kind of finish it off tomorrow itself. If you have some prior knowledge on that, even otherwise, I will try to do some just like so. 2 months we kind of condensed in 2 slides, right? 1 or 2 hours. I'll try to do something like that, some justice, okay, in tomorrow's class. I think this is a good time to stop. I'll see you again tomorrow. Okay, have a good one. Take care.